Okay, thanks everybody. Thanks for your attention. It's a pleasure to give this summary of our project. We're all really excited about it. We even have a few of our team members online today, which is good. Hopefully, technology willing, we'll be able to sort of go through this. Margaret, just let me know if we drop out or something. So I'm going to give just a quick intro to our project, which is called a JWST study of the Starburst-AGN connection in merging luminous infrared galaxies. And you can see on our slide here that this is part of our GOALS project, which is a study of the 200 or so nearest luminous infrared galaxies in the local universe. Put our website on the bottom. And this is a list of all the people, all the co-Is and people which are part of our program. The co-PI is Aaron Evans at the University of Virginia. And as part of this talk, let me give you a quick rundown of what we're going to do. I'm going to give you an intro. I'm going to talk quickly about the basic science and the targets. I'm going to go through the modes that we're using, some of the products that we're going to generate. I'm going to give you a quick status of the simulations and the pipeline work that we're doing, mostly by Kirsten Larson, who's a postdoc at Caltech, and I've invited her to join us today so she can give that presentation as we get a little bit later in the slides. And then I'll show the schedule at the end, just like Tommaso did, of when we're delivering our products. So this is ERS Program 1328, and it's to study the physics of star formation, black hole growth, and feedback in 4 nearby merging infrared luminous galaxies. And it's based on our GOALS survey, which I mentioned before, which is a survey of over 200 LIRGs in the local universe. Our team has 21 co-Is and 8 science collaborators across 8 countries and 18 institutions. So it's a fairly large group by the standards that I'm used to working in. And we have regular discussions and phone calls to keep pace of our project. And for this project, we're combining NIRCam, NIRSpec, and MIRI images and IFU spectra with a lot of ancillary data that we've been acquiring over the years for the GOALS sources, and which we're continuing to acquire, much of which has been published, but not all of it, because it's an active, ongoing project. And these data include data from JWST, Spitzer, Akari, Keck, ALMA, JVLA, and Herschel. And the goal is to sort of measure the interaction of the stars and the gas and the dust on scales of about 50 to 100 parsecs in these galaxies. The total time for a program is about 33 hours, which includes all overheads. We're currently running it through the new version of APT, and the science time is somewhere probably between 7 and 8 hours on source. So because we're doing bright nearby objects, we're overhead dominated for this kind of a program, as will be everyone. So I just wanted to go quickly through some of our basic science. We're interested in answering questions about how stars form and black holes grow in merging galaxies. How do they impact their interstellar medium? And especially, what are the implications for models of fueling and feedback from both AGN and Starburst? And it's good to remember that JWST is going to give us a huge leap in our sensitivity, our spatial resolution, and our spectral resolving power compared to what we had with Spitzer IRS over the same wavelength range in the mid-infrared. And so this will really transform the studies of the sort of dusty ISM and nearby merging galaxies, and galaxies which are just going through some rapid evolution. So it's important to remember that it's kind of exciting that, especially after you see these 2 talks together, that Tommaso is really probing the epoch of reionization in some of the highest redshift galaxies, and we're looking at sources which are essentially in our own backyard. So it's good to remind people that JWST has a lot of power even for studying known objects at very low redshift. And so some of that is what we'll discuss today. So we're going to probe this sort of multi-phase ISM and luminous infrared galaxies on sub-kiloparsec scales for the first time in the kind of detail that we've never had before. And that means that we're going to be able to look at ionized atomic gas heated by young stars in AGN. That's star-forming clumps, narrow line regions, and jets and shocks in all of these galaxies. With MIRI and NIRSpec, we'll be able to probe the warm molecular gas. understand its temperature and dynamics, which is an important tracer of feedback in these galaxies, and we'll also be able to study the dust. And for us, that means studying both the small grains, the PAHs, the polycyclic aromatic hydrocarbons, and also studying the larger grains, which provide the continuum. So we'll not only be able to see where the dust is, but we'll be able to answer questions about how the dust is affected in these sort of active environments. Okay, so here are our targets. We have 4 targets from upper left to lower right. NGC 7469, NGC 3256, BV114, and IRS 08572-39. So these are the 4 nearby targets selected for this program, and they range in properties. And I'm going to go through some of that in an upcoming slide, from an active galactic nucleus on the upper left, which is a Seyfert 1 or 1.5 type, where you actually see the AGN in the emission lines, the broad emission lines, through starburst galaxies and sources which are extremely buried in the infrared and very, very dusty. And it's important to remember, and I think we illustrate that here in this image, that you can see that the red squares are the MIRI IFU field of view, and the blue squares the MIRI imager field of view on each of our targets. And that we're sort of focusing on the nuclear regions with the IFU because that's where most of the action is. That's where we're going to see the AGN, the circumnuclear starbursts, and the feedback. Even though we're going to get a multi-wavelength study through the imaging of the entire galaxies, there's going to be a lot to do and a lot to follow up. So this is sort of a pathfinder. You sort of look at this program as a pathfinder, not only for the study of nearby galaxies and AGN in the local universe, but also even for these objects, there's still, you can see there's going to be a lot more to do and explore. So I'm not going to spend a lot of time here. I've listed some of the basics for each one of our targets, and at the bottom you can actually see some of the references. For 3256, it's a late stage merger. There are two nuclei separated by about 5 arc seconds, which is a little less than a kiloparsec. One is extremely obscured, the southern one. There are strong molecular outflows from both nuclei that are seen with ALMA. And there's abundance of shock gas seen in the optical and the infrared. The southern source probably has an obscured AGN, and there's an extremely large number of superstar clusters that have been mapped in this galaxy, nearly 500. And so we're really excited about using the imaging capabilities of JW to understand the properties of these star clusters in a lot more detail. 7469 is a Seyfert galaxy, which is also a pair, has a supermassive black hole, which is about 10 to the 7th M suns in the center. And interestingly, in this galaxy, there's a Seyfert galaxy, which is surrounded by a very cluster-rich star-forming starburst ring at about 1 arcsecond radius, which seems to have a sort of a bimodal stellar population. So that's going to be very exciting to understand. And it's been mapped with Keck and the VLT and has a biconical outflow in the high ionization near infrared lines. So we're really excited about seeing what that's going to look like with JWST and getting a lot more information on that high ionization outflow. BV114 is a really interesting source. It's called the nearby analog for high Z LBGs, the Lyman Break galaxies. It's a source where most of the infrared emission comes from one of the objects and most of the UV emission comes from the other. It's 2 objects separated by about 6 kiloparsecs. It's extremely luminous in the IR, and it also hosts a galactic superwind. And interestingly enough, it has a lot of shocks which have been mapped, which are at the interface of the merging galaxies, and it's been speculated that there's molecular gas inflow towards the eastern source. And lastly, IR 08572 is one of the original bright galaxy sample ultraluminous infrared galaxies in the local universe. It's a late stage merger. Most of the infrared comes from the dusty northwest nucleus, and it has the deepest silicate absorption that we have in all of the nearby units. It's incredibly opaque and very, very compact. There's crystalline silicates, a powerful starburst, and it's likely from our modeling that it hosts a buried AGN. There are also extremely high velocity outflows seen in the near infrared and the far infrared in this object. And here's the IRS spectra of all of our sources, and you can see there's a wide range from 3256 at the top. This is to 08572 on the bottom, which is highly obscured. And for people not used to looking at these sorts of spectra, this is the IRS spectra from about 5 to 40 microns from the low resolution spectrograph. And you can see in 3256, you see the strong emission lines from fine structure lines. There's H2 emission, and the PAH features are very prominent. And when you go all the way down, you can see in 08572, it's almost completely absorbed, and the silicate absorption implies at least 100 magnitudes of extinction to the very core. The source, the pHs are very weak. There are other absorption features which you can't see in this low resolution spectra, but from molecular species as well. So it's an interesting set of objects with quite a varied range of mid-infrared spectra. And we're very excited about the chance to do the 3D spectroscopy on the source. This is just a cartoon, of course. These are not the spectra of these actual objects. But it's going to give us this sort of 3D spatial spectral view of the gas, the stars, and the dust, and the nuclei of these objects. And it's important to remember that the IRS slits were fairly wide, and so all the spectra I showed you were of the central sources. But our IFUs that we're going to get, our IFU view that we're going to get with JWST, is essentially going to give us a resolved view of everything that's happening inside the IRS slit. So it's going to be quite a wealth of information on those few arc seconds of the central, let's say, few kPCs of every single source that we've never had before at these wavelengths. So here's a rundown of our observing modes. For MIRI, we're doing the full spectral colored from 5 to 29 microns in the 4-point dither pattern, plus our sort of off-source backgrounds. For near spec, we're doing the G140, G235, and G395 gratings in the sort of rapid readout mode with our 4-point dithering, and we're getting our lead cal images for each grating. And for the imaging of each target, for MIRI, we're doing the 560W, the 770, and the 1500. For near cam, we're doing the 150, 200, 55, and 44W, and the latter two basically are mirrors of the IRAC short wavelength filters. And we're doing subarray imaging for 3 of the 4 targets because they're very, very bright in the center. So I think those will be useful not only to get our data in the very cores of the galaxies, which are bright in the infrared, but also for calibrating as part just for the community, for understanding these modes and seeing what they're able to pull out of the centers of very, very bright. So let me run down some of our science-enabling products. We have a multi-wavelength ancillary data set. I mentioned that before. This is very, very important and powerful for us. It includes a lot of high-resolution data, especially from ALMA, from HST, and also ground-based facilities as well. We're going to get, of course, the JWST images and spectral cubes. I'm going to talk a little bit more about that later. We're going to process those data and produce the spectral feature maps, and they're going to provide a very, very important cross-calibration between the JW and the Answerly data sets. And I think a lot of people are interested in that, and that'll be very important to get in the first few months of the mission. And I think the interesting part of our project is that we'll be able to do this sort of cross-calibration in a result sense for sources that have a very large range, dynamic range in brightness. And for a software product, we're reworking our cafe software that we had written for Spitzer that was published in a paper by Jason Marshall in 2007. It fits the emission lines, the dust features, and the continuum in each spectrum. And there's an example on the lower right of one of these fits from NGC 6240. I think this is from my paper in 2006, but you can see the other references there. And we've been tuning this spectral package and doing a lot of modeling on the local infrared galaxies as well, well beyond what we did for Spitzer. And there was a recent paper by Jason in 2018 where he fit one of our ERS targets, which is IR 08572. And we're going to adapt this to the JWST wavelength range and resolution, and we've already started to do that, and we're going to deliver the software as part of our ERS program. And I'll come back to that also. So here's a list of the updates we're doing to CAFE. I think I'll go through this quickly. We've updated this to work on the Akari and the Spitzer data, because Akari goes down in wavelength, and it's a good analog for what we're going to get with JW. We made it a lot more flexible to cover any spectral resolution. Remember that it was written for the Spitzer data, which was R of 100. And now we're getting down to 2,500 feet 1,000. So we've updated that. We've expanded the spectral fit. I mentioned that already. We're including all the lines that are in the new wavelength regime. We're including a much better treatment of the 3-micron PAH feature, which is highly absorbed, and actually consists of multiple features, which we didn't fit before. We're adding options to use custom opacity profiles. We're calculating the emissivity of the grains in a different way, and we're adding a resolving power-based weighting scheme for doing the best fit, and a configuration files have been updated for running the model. So we've done a lot of work already for adapting the software. We have a lot more to go. We have to do a lot more testing. We're in the middle of that right now, especially using simulated spectra, which Kirsten's going to talk about. She's actually generating the spectra, which we're going to run through the CAFE fitting as part of our sort of end-to-end testing. We're going to convert the program from IDL. It was natively written in IDL. It's going to convert that to Python, and we're going to adapt it to be able to fit the spectral cubes to create the spectral line images, which we're going to deliver for each of the targets. Here are 3 examples of some of the CAFE fits in a paper that's in preparation now. This is the updated version of CAFE, just to show you the varieties of spectral features that we're able to fit. From the upper left is a source that has strong pHs and fine structure lines in the mid-infrared, and the source in the middle is AGN dominated source. You can see that the lines are much smaller equivalent width, and there's a lot more hot dust, and it's not very obscured. And the source on the lower right is just highly obscured source, where you can see incredibly deep silica absorption at 9 and 18 microns. These are just some examples from this paper by Buffini et al. That we're working on right now. Okay, so Kirsten, if you're on, do you want to take the next few slides and talk about some of the pipeline tests that you've been doing? I can advance, just tell me when to advance it. You have to unmute yourself. And
yes.
Okay,
can you hear me now?
Yeah, that's good.
All right, yeah, so I've been working with MIRI simulations to make a simulation of what our IFU cubes will look like, and then running pipeline tests with the current beta versions of the pipeline. So the goals of this was so that we could simulate what, say, a star-forming disk galaxy would look like with a bright nuclear AGN in the center, and then varying the strengths of the AGN so we can test our ability to sort of pull out the differences with the different strengths of AGN and disentangle that from, say, the star-forming disk. So what our goal is to create a fully combined data cube with all 4 of the channels that we're going to be observing with JW, and then get a pipeline-generated spectra so that we can test this updated CAFE software that we just talked about. So a lot of these are still, a lot of the MIRISim and pipelines are still in beta, so we're clearly still having some issues. So currently there's some trouble getting the MIRISims and the pipeline programs to work together. And there's still some known issues in the pipeline, but it's kind of difficult because there's not yet good documentation online, since it's in beta version, of what parts of the pipeline have issues and all of the workarounds with them. So I've been working with people, messaging back and forth with people at Space Telescope, David at Space Telescope, to find the best workarounds to get things to work. So this has some details on how we're getting things to work around the current issues. So the newest version of MIRISim that I'm using doesn't have updated reference files. And this is important because the pipeline version does have the updated reference files. And so you have to change the MIRISim to use the same reference files. Otherwise, it breaks because the pipeline is expecting the new reference files. So that's the first sort of workaround you have to do. You have to add in the new reference files and then sort of hack a few lines of the MIRISim code to use those same reference files that the pipeline is expecting it to have. So after you can run your simulation using that, then you get to the pipeline, which does have the new version of the reference files that Space Telescope wants it to, which is great. But like I said, the pipeline's still in beta mode, so it's got a few issues with cosmic ray subtraction and still finding all the bad pixels. So these are sort of the example of the sort of technical workarounds that you need in the pipeline in order to get it to run through. So there's sort of 3 steps to the pipeline. So in the step 1 of the pipeline, you have to turn off the reference pixel subtraction. In the step 2 of the pipeline, you have to turn off the stray light step. And in order just to make things run in a reasonable amount of time, we're also turning off a cube build step in step 2 and waiting for step 3 to do that. And right now, if you just run spec 3 pipeline, the step 3, it doesn't work. So you just skip the step 3 and just cube build all of the data yourself with just the cube build step. And then currently we have to do manual source extraction. We don't have it running yet to do sort of the pipeline produced source extraction. So there has been updates to the pipeline. So previously there was issues with the cube build properly combining all of the channels together. This should be fixed, but we're still working through some issues, which I can show you.
Let me interrupt you just for a second, Kirsten.
Yeah, please do.
And just tell everyone, we thought it would be useful here just to quickly sort of go through a couple of these. We just have one more slide on this.
Yeah.
And we're happy to sort of talk in future meetings, either of the ERS group or in a wider audience, just of sort of our experience of what we're doing right now, because we're trying to sort of push end to end, starting all the way from the simulator through the pipeline and then using the CAFE software. So this is what we're trying to do now. So we thought it would be useful for Kirsten to sort of just quickly go through some of the successes and even some of the failures that she's having, and then we could talk about those later. Okay, yeah. Kirsten, I think this is your last one, so why don't you go ahead with this?
Yeah, this is. So this is an image of basically a bright point source AGN just for testing purposes. So this is what it looks like when it's gone all the way through the MIRISim and then through the pipeline. So the top one on the right is when we do cube build of just the long band, so not the long, short, and medium together from MIRI. And that looks good. No cosmic ray issues. But the continuing issue we have is when we try to combine, say, all the long, short, medium bands and channels together, there's some issues in the cube build to get one final large cube build. So in the bottom left corner, like cosmic rays come through, those sort of other bright things that aren't in the nice clean top image. And then these sort of overlap regions in wavelengths where, say, the short, the medium, or the long bands are overlapping, you can start to see some like mismatches in the PSF, which would cause some issues in the shapes. So this should just be a point source. And so you can see there's some mismatch in the PSF going on that could confuse some shapes. And there's also a bad pixel there too. So this is just an example of some of the issues we're still working through in the pipeline step, so that we can have this sort of final data cube that we can now hopefully run through and test our CAFE software for the analysis as well.
Okay, thanks a lot, Kirsten.
Yeah.
That's really good. Okay, so I just wanted to give people just a quick sort of table view of our products. I mentioned the products before. We have for our deliverables, we have just basically the calibration data and the data analysis, and I've sort of staggered the notes on the left are just to remind everyone where we were, because I'm just putting all of our deliverables in terms of the launch date on the far right, and we have sort of a set of staggered deliveries just like every other team. Leading off with our sort of calibration and data analysis, followed by the ancillary science data, which we're going to deliver for each target, which are cleaned up images over the JWST field of view from all of these sources, the ALMA, JVLA, the HST, and the Spitzer and CARI images and spectra. Some of those have been published, some of those have been delivered to their respective archives already, but not all of them have, and they certainly haven't been extracted, cleaned up, and line maps made for every single source that we're delivering. So that's part of that. There's, of course, the JWST science data, the cubes, the 1D spectral fit, the 2D feature maps, and the feature maps that we make from our CAFE fitting software. And then we're of course going to deliver the CAFE software and the relevant documentation as well. I think that's our last. So yeah, that's my last slide. So thank you for your attention. I'm happy to take any questions now that you have. And like I said, Margaret, we're happy in future iterations, either of the internal group or just in a wider audience, for talking about some of the technical issues that we're running into, the successes and sort of the struggles that we're having doing sort of these end-to-end tests. Thanks.
All right. Well, thank you for that very informative talk. I'd like to encourage people to unmute, either offer a comment or a question. Well, I have a comment and question. First of all, the comment is that these ERS teams are heroes because they're on the bleeding edge of everything that's being produced at the Institute in terms of pipelines and stuff. And the feedback they're providing the Institute will be very useful in future iterations of the pipeline as we progress towards launch. The question I have is, every time I talk to people about the IFUs and doing spectra, the thing they worry about most is matching the spectra and trying to get a good, if you will, relative spectral response. Can you talk a little bit about your thoughts or concerns about that?
Is that a question for me or does everybody?
That's a question to you and I guess Kirsten. Okay,
well, that's something we struggled with that a lot with Spitzer. Just you could see that in many sources. Spitzer had two low resolution modules and two high resolution modules, and the low resolution each had two components as well. So we often found spectral mismatches, and it takes a long time to work those through. So I think with JW, that we're going to have, because the IFU fields of view are not necessarily, or not the same, we're going to have the regions where everything, I hope, matches up in the center, and then you get differences as you go to the edge. And I think one of the things that we're going to try to calibrate with our data is how well we can piece together these sort of multi-component spectrum. I'm sure there will be well calibrated by looking at point sources, and we're going to have to see how well we can do with the resolved sources. And that's part of the reason why we actually wanted to do this on some of these targets, because we'll get this information really early. And the targets have a wide range of properties, from very compact, very red sources to much more diffuse objects with lots of star clusters. So I think it'll give us a really nice data set, both for our science and both for the Institute, to hopefully tackle some of these problems that we're undoubtedly going to see. I don't know if that's a good answer to your question.
No, that was great. For the line list, do you use a particular line list data set when you do the spectral fits?
Yeah, there's a line list which is included in the CAFE software, which is based on the Spitzer and Akari data.
And is it specialized to your suite of objects like the AGN and star formation, or does it have a wider?
No, it actually covers. It should cover everything that we've actually seen in all of the targets. I mean, we run this on over 200 sources, so there's a wide variety of spectral types. I mean, but the features are basically mostly the same. So it includes. Yeah, it includes defined structure lines, it includes the pHs, it includes the broadband dust absorption features, it includes molecular absorption features. It also includes ice features.
So someone could, for example, use this in a star formation region.
Yeah, you should be able to use it now. I think one of the things that we're interested in is how well we can do at this sort of 3 micron range, because in the range where we're going to have where we're outside of the Spitzer realm, but where we're going to have exquisite sensitivity and spectral resolution, we should, that's where we're going to see the new things. And so we have a little bit of hint of that from the Akari data. But these should work, and we'll be able to fold in different templates for the absorption profiles as they become available, and people should be able to do that. So that was part of the note I had in there, with sort of making it a little more flexible in terms of reading in your sort of own absorption. And I think around 3 microns and 4 microns, that's where people are going to be most interested in doing it.
Okay, does anyone have any other questions on the call? And I had one more curiosity question. So the spectral resolution for James Webb is, a factor of 10 or 100 more than we've had before. What are you most excited about in terms of what you might discover because of the spectral resolution?
It's really, it's compared to the low resolution spectra I showed, it's much higher, but it's about a factor of 5 higher than what we saw in the ERS high-res data. And I think there's a couple of things that are the most interesting for us. One is we're going to get the line profiles. So because a lot of our sources have evidence for outflows, we'll actually be able to track those outflows on spatial scales and spectrally in a way that we could never do before in the mid-infrared. Now, we can do that in the near-infrared from the ground using things like Symphony and OSIRIS. And we have been doing that, and other people have done that very successfully. That's how we know that there's fast-moving gas in these objects. But I think with JW, we're going to have the opportunity with MIRI to do it in the mid-infrared and get much deeper into these dusty regions. So that's really exciting. The other thing I think for the AGN is that you'll be able to sort of see the width of these lines and how they respond to the black hole. And so there have been papers that have gone through heroic efforts to measure the line width of some of the high ionization lines that you see in the infrared, the mid-infrared, and correlate those with the black hole masses. I think we'll be able to do that a lot better, because remember what we're going to get with JW is we're going to actually be able to do a much better separation of the regions immediately around the AGN with the star-forming regions at 500 parsecs or a kiloparsec away. So I think it's going to give us a lot of information spectrally in terms of the kinematics of the gas responding directly to the black hole, and the gas which is responding to either infall or these sort of starburst-driven outflows that we've seen on much larger scales.
All right, very good, Ben.